Hello and welcome to yet another video of Cornerstones of Math. In this video, I gave a little tweak on the famous grid problem. The top right figure shows the path network of 3x4 grid with upper right diagonals added to each square. You want to move from point A, bottom left, to point B, top right. Problem A is the original grid problem, also known as shortest path problem. If you can only move either up or right, how many ways are there to move from A to B? And in problem B, there comes a tweak. If you can move either up, right, or in upper right diagonal, how many ways are there to move from A to B? By the way, it is worth mentioning that this doesn't just mean the shortest path. And in problem C, can you generalize the result of problem B to an arbitrary m by n grid, where m is the smaller number? Alright, let's start with the first problem, the original grid problem, where you can move only up or right. Many of you may already know how to do this, so I will be quick on this one. First, let us introduce the notation R and U, where R means moving right by 1 unit and U means moving up by 1 unit. In order to move from point A to point B, U must move right 3 times and up 4 times. Therefore, the number of shortest path is the same as the number of ways to arrange 3 R's and 4 U's in a linear manner. This can be done as follows. We have 7 elements in total. So first, let us just arrange these 7 elements as if they are all different, which gives 7 factorial ways. However, these 3 R's are indistinguishable, meaning that we have a total of 3 factorial duplications. Likewise, these 4 U's are also indistinguishable, meaning that we have additional 4 factorial duplications with U elements. This gives 35 ways. Let's move on to the next problem, where up, right, and upper right diagonal directions are allowed. Just like the previous problem, let us use letters to denote directions. R for right, U for up, and additionally, D for diagonal. We must introduce one more parameter called X. X is the total number of movements, which in this problem is not fixed and can change. So, what values can X have? The obvious one is 7, meaning 3 times right and 4 times up, and no diagonal movement. But what would happen if we include one diagonal movement? Well, you can easily find out that in that case, the total number of movements becomes 6. If we add one more diagonal movement, then the total number of movements becomes 5. And if we add one more so that we have maximum number of diagonal movements, that is 3 diagonal movements, then the total number of movements X becomes 4. So X can have values of 7, 6, 5, and 4. Let's take a look at these cases one by one. First, the total number of movements is 7. This corresponds to moving 3 times right and 4 times up. Therefore, the number of ways is 7 factorial divided by 3 factorial 4 factorial, which gives 35. Next, X equals 6. This corresponds to 2 times right, 3 times up, and 1 time diagonally. Therefore, the number of ways is 6 factorial divided by 2 factorial 3 factorial, which gives 60. Next, X equals 5. This corresponds to moving right once, up twice, and diagonally twice. Hence, we have 5 factorial divided by 2 factorial 2 factorial, which is 30 ways. And finally, x equals 4. This corresponds to moving up once and diagonally 3 times. So we have 4 factorial divided by 3 factorial, hence 4 ways. Therefore, the total number of ways is 35 plus 60 plus 30 plus 4, which is 129 ways. At this point, the generalization is pretty easy. We think about possible values of x again, which denotes the total number of movements. Again, let's start with the zero diagonal case, which gives the largest value of x of m plus n. If we add a diagonal movement, the total number of movements decreases by 1 as you saw in the previous problem, resulting in total m plus n minus 1 movements. So x decreases until we reach the maximum number of diagonal movements. The maximum number of diagonal movements is the smaller number between m and n, in this case m. This means that we have m diagonal movements, and all that's left are upper movements, which there are n minus m of them. That is, the smallest value that x can have is just n. So these are the possible values that x can have. Each of them corresponds to: first case is moving right m times and moving up n times. The second case corresponds to m minus 1 rights, n minus 1 ups, and 1 diagonal. And the last case is n minus m ups and m diagonals. Let us deal with everything all at once by thinking about the case where x equals m plus n minus k, where k can have values from 0 to m. This is the case where we have k diagonals. Or more specifically, m minus k rights, n minus k ups, and k diagonals. This case gives m plus n minus k factorial divided by m minus k factorial, n minus k factorial, k factorial ways. The total number of ways can be obtained by adding up this term from k equals 0 to k equals m. So we have this sigma m plus n minus k factorial over m minus k factorial, n minus k factorial, k factorial ways. Here, the m in the upper end of sigma is actually minimum value between m and n if you want things to be even more general. This is as far as we can get in terms of simplified expression. And that's all for today's video. Thank you all for watching. Please don't forget to hit the like and subscribe buttons if you enjoyed this video, and I will see you in another video.